Okay, let's get this over and done with. So just done recursive relationships between the same or different instances in a entity of an entity. Relationships can involve more than two entities. So for example, here's an example of a ternary relationship, which is called a transaction. So here we've got a project, some kind of project that's being done. We've got a contractor involved in it, somebody you're paying to do the job, and you've also got a contract. So the whole thing, the relationship, the transaction involves a project, a contract, and the contractor. So you can have ternary relationships, you can have quaternary relationships, whatever, quinternary, whatever it goes up to. Relationships have what we call cardinality, which is the numerical relationship between the two entities in a relationship, or between the entities in the relationship. So the classic ones are these three: 1-to-1. There is one record in employee matches one record in department. An employee is in one department. Each employee is in one department. However, you can also have 1-to-n relationship. Oh, sorry, managers in this case. We've got a relationship. So an employee manages a department. Each department only has one manager. But a department has many employees who work in the department. So there is one department and many, which is either represented as M, but is often used as N. So it could be N, it could be M, because what we call it is an N to M. It's often called an N to M relationship, a many to many relationship. So you have one department with many employees. Maybe we have projects where there are many projects worked on by many employees, and each employee works on many projects. So that's an M to M, or in this case, N to N relationship. An employee can work on many projects, or a project can involve many employees. So those are your sort of classic three. But in modern terminology or syntaxes, we often sometimes get more complex, or not complex, but more subtle relationships that we can define. So some relationships maybe have what we call partial participation. A partial participation relationship is where one of the entities, the relationship may not exist for the entities. So here we've got a building and then a postcode. So all postcode, so each building could have, that should actually be 0, 1 there. Can either have 0 or 1 postcode, perhaps. So the 0 indicates that you could have no postcode. So the university here, this campus, is made up of several buildings. We all have the same postcode. We all share the same postcode. So a building itself could maybe not have a postcode specifically. Think of a shed. Think of a cattle shed in a field. That's a building, but it doesn't have a postcode. Yep. It's a better example than a university building. Full participation means that the relationship has to exist, or the entities have to exist, share a relationship. So a student at the university, each student has to be enrolled on either 2 or 4 modules, depending on whether they're part-time or full-time. Yep. So either 2 or 4, you can't have 0, you can't have 6, you can't have 5. You can only have 5. So basically you can designate actual numbers onto your cardinalities. Cardinalities are often represented as numbers, but there is also graphic styles, and indeed they started off as graphic styles. Here's a number of the different notations. So I did mention that there are a number of different notations that are used on entity attribute relation diagrams. Here are some of them. So a zero or one relationship, one to many. In the crow's foot notation is drawn like that. So that's a zero or one relationship. A zero or many relationship, this is the one you'll probably see more often, oh God, is this one with the crow's foot. That's the many end, that's the one end, the dot indicates the zero. You can see there is arrow notations, Bachman notations, ADW notations, Oracle notations. There was a whole variety of different notations defined most by things like different software companies, different software development companies. So bear that in mind. There's a whole variety of notations, they're all meaning the same things out. Now we've got now three things that I think are like the extras of entity relationship modeling. We've done the basics, but if you go and you see an entity relationship diagram, you may see these symbols on them. I don't like them. I think they tend to be used more by the database developers than the designers coming up with the database design, if you understand the difference. So a designer would be a domain expert or somebody whose specific job is to interface between the users and to come up with a design on the basis of the data that's availability and what the users do and things like that. The other option is coming from the IT side, the people who deal with the databases and what they want to do. And sometimes I think they have different approaches to how and what information they put on entity relationship diagrams. Anyway, you may see these. Let's not worry about the detail of them, but I thought I'd show them anyway because you will see them. Sometimes you get a double boxed entity, and that indicates what's called a weak entity. A weak entity. What's a weak entity? A weak entity is an entity whose primary key is derived from other tables or other entities. So it doesn't have its own inherent primary key. So here's an example, an authored book. An authored book has two fields, an author ID and a book ID. Both of these are foreign keys. One comes from the author's table and one comes from the book's table. The primary key for this table is a composite key made of author ID and book ID. Okay? So the primary key is derived from other tables, therefore it is a weak entity. A strong entity has its own primary key. You may also see double boxed, double diamonded relationships. Now, I think it was on Monday, I spent probably half an hour in trying to understand whether there really was a difference between a weak entity and an identifying relationship. And frankly, I couldn't work it out. So, as I say, minor thing, but you may see it. So what is an identifying relationship? And the entity's primary includes a foreign key from another entity. So that definition is almost the same as the other one as far as I'm concerned. And I think they are the same as far as I know, can tell, but it's the way that they're drawn. Remember I said you can draw the same model with a different diagram, entity relationship diagram. So in this case, the authored book is not being regarded as an entity, but as a relationship. It's the same, when you turn it into a database design, it's going to kind of explode into the same thing at the end of the day, but it's just compressed in a slightly different way here. So in this case, yes, author ID and book ID are foreign keys. Author book has an identifying relationship with both author and book. So we can draw exactly the same relationship using different relationship diagrams, ER diagrams. I find that quite confusing. I don't like it, but it's what's out there. There are also wonderful things called associative entities, which are defined as a table that defines a relationship. Well, that's the same as authored book, isn't it? That's a table, because it's going to be a table with the book author ID and the book ID, that is a relationship. So it can be drawn like this as well. But to a certain extent, I think, why don't we just do authored book, and then have the maybe we've got attributes, or the foreign keys, we've got the primary keys, we could draw it like that. So that's about 4 different ways to draw the same relationship and the same in an ER diagram. So just bear in mind, if you've seen these funny symbols, that's what they are. There may, for database experts, be a technical difference between them, but I couldn't work it out if there is. Okay, that's your EA design. There are, however, some design issues to consider. First of all is one we've already seen, alternative notation. So here from this paper in 1995, there was a list of that number. They'd identified at least about 10 different notations. There's probably more than that as well. People tend to be, it's rather an ad hoc. There's no standard way of drawing an ER diagram. Chen 76 was probably the original, well, it was the original, I know, of course it was the original. But it was it used these forking graphics, it's got the lollipop blobs for the attributes. It actually takes a lot of space on the page to actually show quite a lot of information. So I think other styles have to a certain extent evolved to be more concise and better so. So often you just see the table name and then at the top of a box, and then the fields listed in the box, and that's far more space efficient than all these lollipop bulbs. So different diagrams. So there are lots of different notations. You might see diagrams drawn in lots of different notations. Another issue is size and complexity of diagrams. So for the toy databases that you're dealing with, or they're toy, they're not really quite toy, but I mean, they're quite small databases compared with corporate IT systems and things like that. You can draw your ER diagrams, chances are everything you'll do in this module you can draw on an A4 piece of paper. As we'll see for UML diagrams, ARC, as an example, it's just because I'm not familiar with giant, I'm familiar with giant UML diagrams, but not giant ER diagrams. So the ArcGIS, when ArcGIS was at version 10, which must be about 10 years ago, no, sorry, 10, 15 years ago, you used to be able to get the diagrams for the database design and the software design, and they would be on AO sheets, and I think there were about 10 of them. So an AO sheet of paper, twice the size of this, 10 sheets, twice the size of that. And it was still, and you had to follow this entire model across these multiple diagrams. So there are real problems with drawing diagrams of large systems. And the most normal approach is to split into multiple diagrams, to have high-level overview diagrams, more detailed low-level diagrams of lower subsystems. So break your giant system apart into subsystems, lower systems. The other problem you've got is the problem of information density on these diagrams. So I've already mentioned the fact that the lollipops and things I don't think are very efficient. Put it like this. If you took a ER diagram, I reckon, and showed it to, I don't know whether any of you have heard of Edward Tufte. He's the sort of one of the gurus of information design. You took one of those diagrams and you showed it to a modern, graphic designer, somebody interested in information aesthetics, they would rip it apart. It's about the most incredibly wasteful when it comes to ink to information ratio in ER diagram. Awful. So you've got all this stuff, these lines and things that are just visually causing confusion in your brain, unless they're particularly well laid out. So watch out for information density. The fact that you've got lines going in all over the place. It's not easy to read these diagrams sometimes, especially when you get into ternary and large relationships that involve 3, 4, 5 entities. You're trying to squeeze all these entities, connect them into a diamond, possibly with roles written on them. It's not easy to do. It's messy. And the other thing I've got there is, do your readers need to know about weak associative arrays and identifying relationships? In my opinion, most of the time they don't. So it's not worth bothering about that. Just keep them simple. Keep them simple. Great. ER diagrams were designed for the relational model, and we know the relational model doesn't include space. How do we extend ER diagrams? Can we extend them for spatial entities and relationships? Taking things even further, what about temporal relationships, relationships in time, and things like relationships in scale, geographic scale? Well, I'm not going to answer, well, I am actually going to answer the scale one and the space one. I'm not going to do the temporal one particularly. Okay, so spatial data type is an attribute of an entity. The entity is represented by a point, a line, a polygon. Excellent, great. So geometry, or the geometric representation, is an attribute of an entity. But what about spatial constraints, spatial relationships? Now, be careful with the difference between a spatial relationship. I'm likely to use the words interchangeably. But a spatial relationship is simply some sort of description about the relationship of two objects. So I could say the photocopier is, 4 meters to my right. That's a relationship, spatial relationship. But it's not a constraint. I'm not constrained to live within 4 meters of a photocopier, and I can't go anywhere else. It's not like I can't move anywhere else. So we're talking about constraints here, rules, spatial rules. So if we're talking about a pipe network with valves on it, the valves have to be on the pipe network, physically connected to the pipe network to be part of it. So you have to have a topology relationship that X is on Y. Yep. Okay. All the schools in a local authority have to be within the local authority boundary, let's say, so that X must be within Y. You wouldn't allow a school to be entered that's in another educational authority area. Local authorities never overlap each other, not at the same hierarchical scale anyway. So districts, so London boroughs, no place in London within the boundaries of London, whatever that may be, of the administrative districts, is either within more than one borough or is not in any borough. Yep. The boroughs form an interlocking tessellation in inner London. So we could have a rule there that the boroughs don't overlap each other, not allow any overlapping. Perhaps you can have proximity relationships. Perhaps I'm only allowed to put in a traffic measurement strip within, say, 20 meters of a pedestrian crossing for some reason. This is to do with the rules of whatever you're trying to measure on the cars. So you put a constraint in the database so that your measuring device must be within, 20 kilometers, but it doesn't matter. The principle matters of something else. It has to be within a distance of something else. And that's a rule, not just a coincidental relationship. So this is the suggestion in Shakur, and I've seen it in other, the book Shakur, I can't remember whether it's Shakur or Shakur, the one I recommend, but also I've seen it elsewhere. I'm not quite sure whether its origin is. I was meant to look this morning and then forgot. So I'm not quite sure what its origin is, but this seems to be the one that's used most generally, although I must say I don't think spatial entity relationship diagrams are that common, to be honest. I don't think they're drawn that often. Be interesting to see who's using them and where and when. Anyway, so the proposal is you have a little pictogram in the top left corner of your entity box that shows the geometry associated with that entity. So at the top there, dead easy. So we're talking about We've got pipe networks here. So a valve controls the flow in the pipes, is a point object. The pipe is made of lines, is a linear object. The tank, the water tank, the storage tank is a polygon object, hence that sort of squashed polygon shape. Now, as you hopefully know, there is a difference between, objects. If you think in ArcGIS or any GIS, you can have a record in your table, and then you have associated geometry with that. The geometry may be a simple one. There might be a one-to-one mapping between your entity and your geometry. So there's one point for each city. There's one line for each road. There's one polygon for the city boundary. But often that's not the case. And you have what are called multi-part geometries. Have you come across multi-part geometries? A multi-part geometry is a geometry that's made up of different bits, separate bits, for example, or it's several lines, for example, that combine together to create one entity. So a river, if we're talking about a river in our database may be something like the Thames. The Thames is a very long river. And maybe for convenience sake, we've broken the line representing the Thames into several smaller lines, sections of line. So in fact, the River Thames has a cardinality, the entity has a cardinality relationship with the geometry that represents it. So in this case, a river like the Thames may be made of one line or many lines. So there can be a 1-to-n relationship between river and the geometry that represents it. Country, 1-to-n relationship. Why do you want an 1-to-n relationship with countries? Well, countries have islands. We're a prime example. We're made up of 1,000 plus islands. And there also are the occasional enclaves within other countries. So where I did field work in the Pyrenees, there was a Spanish enclave, which was a Spanish town totally enclosed in France. And these are sort of historical anomalies. So quite often we may need to represent countries with multiple polygons. Down here, sometimes, remember calculated fields? Remember you calculated the final geometry, the final grade of a student from the grades in their modules. And we used a dotted line to represent that in an ER diagram. We can also have derived geometries. So in this case, the river is is represented as one line, but it's been derived from other information in the database. And that's what this is that a rhombus? No, that's a parallelogram represents. Derived. Sometimes you have more than one representation for the same object. So here we have a city. We want to represent a city. We have it represented as a polygon, but we also have it represented as a derived point. So we can either use the polygon or the centroid of the polygon, which is derived from the polygon, to represent the city, the location of the city. Finally, we've got a couple of others down the bottom here. We've got this star, which represents any shape. So the report might include a city item, a river item, a valve item. And this exclamation mark, which I did look up, which means user defined. I can't think off the top of my head why you might want that. So that's how you represent the geometry, one way of representing the geometry and the cardinality relationships with geometry in an ER diagram for entities. What about relationships, spatial relationships? Well, again, the suggestion is to use these pictograms. So, on the left-hand side, we have routes. We have a road network which is made up of routes. roots being individual lines. They combine together topologically, insert some kind of, now, the rules as to how to put lines together to make a network depends on what the network is. So there are a variety of set of rules that might be applied, but basically you're imposing a relationship that makes the lines part of the network. And we can use, I suggest using this tree-like symbol to represent that topological relationship between the lines and the derived networks. This one's maybe easier to understand, is the example of a nested administrative regions, whereby counties, it says country, but it should be, oh well, it's country, it can be country, that's fine, are embedded within regions. There's a hierarchical relationship between the regions and the counties. Counties are nested polygon relationship. Countries must not overlap each other, and also they must be embedded hierarchically, spatially within the region objects. All right, really finally. Okay, so that's your entity relationship modeling. Now we're just going to really briefly look at UML, and I'm really just straight through. UML is a logical modeling approach for the object model. They use similar diagrams to ER diagrams, but they're called class diagrams with a different notation. And as I say, we're going to have a whole lecture on objects later on. But importantly, I just wanted to put this in, I thought, because it's not just used for data modeling. UML diagrams are used for every aspect of system design. So you might be doing ER modeling for your database design, but may use UML for some other part of the design of your system. So they include systems, standardized systems for depicting things like user interaction and temporal sequences, events, and things like that. That's kind of what they look like. That's a lousy slide. I haven't found a decent example yet that shows them all. Not going to go into any details. That's what they look like. And they model things. So the one we're interested in, which is the class diagram, models the relationships between object classes in a class hierarchy. Let's not go into the details on that. Okay. This is the sort of key. This is what I was saying earlier, the UML diagram for the ArcMap object model. This is just the key, explaining how the diagram operates. This is just one small section of the overall object diagram for the ARC8 core geodatabase object diagram. So I would say that was about, the overall model is 40 times larger, top of my guess in my head. They've actually stopped publishing these. These are not available anymore. They've become so cumbersome that Esri has stopped making these. This was the last one ever produced. So for the last 10 years, they have never published an object model diagram of the ArcGIS software and the objects that are used to create it. Partly because I think it's just so cumbersome to actually manage and draw these things. Okay, summary, just the end. Data modeling is an essential part of systems design. Conceptual model provides an overview. The logical design is an on-paper implementation. ER diagrams are a tool to facilitate and document relational designs. And we'll talk, next week, we'll talk about the tension between facilitating design and documenting design, because the two are not always the same thing, or don't always end up in the same location. And we've seen UML diagrams really briefly are a tool that documents object model designs and concepts. We'll see much more of object design later on. Final thing to bear in mind is you draw these diagrams. These are meant to be, according to the database or the systems, the IT people's view of logical diagrams is that they should fully specify a design. The reality is that they often don't fully specify one. But taking that model, that the logical model should fully specify a design, what that means is that you can use automatically turn an ER diagram or a UML diagram into a database or software design. You press a button You automatically identifies the entities, the relationships, turns those into tables, and creates your design from your UML diagram or your case diagram. Oh, sorry, your ER diagram. And the software that does that is called case tools, computer-aided software engineering tools. I'm not going to say anything more about them apart from, if you want to have a look at a case tool, ArcGIS has one. Dig it out, have a little look at the ArcGIS case tool.